But I would move on without any questions at this moment and would like to invite our next speaker. How many you have? Okay. Who is Arnaud Re. He is a graduate from École Centrale Paris, and he holds a PhD in geosciences from Sorbonne University from 2021. He has first worked 4 years as a research engineer at BRGM on CO2 storage, before then joining GeoStock in 2012, and has there worked on many industrial and R&D projects for storing natural gas, compressed air, and more recently also hydrogen in salt caverns. And has been the innovation manager of GeoStock for 4 years and is since 2020 the deputy director of GeoStock Green Storage. I think many of you will know him from Hystories. He has been coordinating this European project, which recently, I think, was completed. And in this presentation now, he will give a summary of the main findings from these projects. So thanks, Arnaud. The floor is yours.
Thank you. Thank you, Karin, for the introduction, and good morning, everyone. So I will also have a challenge. This is to present this project in 20 minutes. It's 267 man-months of work, I think. So it's 22.5 man-years, half a career in France, at least. So it will be kind, and I'm not the only one that is behind the work, so I cannot enter into details of all of it. But I will try to give you an overview of the way we worked, the findings, and also to try to put them in context. Does it work? Yes. So the context of this project is it started with a call for research proposals launched by the Clean Hydrogen Partnership of the EU on, in the context, of course, of net zero energy. This big ambition, we often forget the impact it has, being carbon neutral by 2050 in the European Union. Huge change, huge shift of the energy system. And the call was about storing hydrogen in porous media. And oh, there is a screen here, great. And so we built the project under 2 ideas. First, that it has never been made at the time, and pure hydrogen was never injected and stored in porous media, nowhere. And there were some technical developments that were needed, and these technical developments were the first part of Hystories, focused on porous media only. And the second part of the project is that this is an infrastructure business. It takes decades to develop, and a project is a €1 billion project usually. And to make this kind of decision on investing on it, decision makers have to have a clear view on the impacts, on the business plans, etc., before making such move. So the second part is about giving insights to decision makers regarding storage demand, environmental, societal impact studies, case studies, to try to help them making such decisions. And here we cannot take out salt caverns, we would miss a big part of the picture, so we consider both salt caverns and porous media in this second half, I would say, of Hystories. So this is, and the overall question at the end is, how mature is hydrogen storage? So you find in this picture the 2 legs, the 2 pillars of Hystories. First part, technical developments. Second part, on green on the left, techno-economic feasibility studies. About the technical developments, we've got the first work package on geology and building a geological database. And we worked at European scale. And for that, we had to involve in the project 17 geological surveys or research institutes from 17 European countries. So we really worked at European scale here. That's why we are so many people in the project. In the work package 2, it's managed by GeoStock. It's about reservoir engineering related to that. And the big part of the work was to build capacity estimate for each porous trap. Work package 3 is work package 3 is about, we discussed it already a lot, and we'll continue doing that, about the microbiological activity that could be found in porous media. So we have also in Hystories 13 advisory board members, mostly gas storage operators in porous media. And we have them in the project because one of the approach was to take samples from a large number of sites, and they besides advices, they also sent us brine samples from their site, and the idea was to characterize these samples to test the development of these microorganisms with this brine coming from these samples, not in the idea of giving them, each storage operator, a result for their site, but in the idea that this natural gas storage site could have been in other conditions, in another energy system, selected probably as a hydrogen storage site. So this was a driven idea of having such a large advisory board in this project. And work package 4 managed by University of Leoben was about material selection and corrosion and hydrogen embrittlement of well casings. And here I've done about the presentation of the first pillar, what we identified and what we worked on the technical developments. And if I move to the second pillar, techno-economic feasibility studies, here we have salt caverns and porous media. We started with the work package 5 managed by LBST, try to identify what are the storage cycles that are relevant and what is actually the storage demand in Europe for underground hydrogen storage. And to do that, they had a kind of economic approach. They modeled all the cycles, the energy system, and they minimized the cost of the energy system by introducing hydrogen storage as one of the technical solutions. And so they match at each time step the energy supply and demand with this hydrogen buffer as one of the options, and they found this kind of results. Work package 6 managed by FHA was about giving insight on regulatory framework, social and environmental impacts, and work package 8 was on case study. So I will go briefly, one slide per work package, so it's not a lot, to present you first technical maturity of porous underground hydrogen storage, then techno-economic findings and maturity of it, and then I will go on the implementation plan we kind of proposed or worked on, and what tools can be used for planning underground hydrogen storage in Europe. About technical maturity, so this work package 1 was on building a geological database. So the state of the art is that there was actually no European storage and a European-wide database of porous traps that could be selected as candidates for underground hydrogen storage. There was European-scale databases, mostly built around CO2 geological storage, notably through CO2 Stop or ETSMAP projects, but it was not really focused on hydrogen. And also it was much focused on porous media and not much looking at salt deposits, and when it was looking at it, it did not have the latest salt deposit databases. So the biggest development, it's public on BGS website, it's a GIS. It lists it includes more than 800 traps with all the geological characteristics that could be publicly found by all these geological surveys. They did quite incredible work, and they have to be deserved. We don't see that much when we just see the result, but there's a lot of work behind that to gather all this data. And so it is published and publicly available on this website. It also has the latest salt deposit data from SMRI, so you can see both in one GIS. And so this is probably one of the main developments that has been brought by the project. It did not really exist like this before. There are still gaps. Data is uneven. It really depends on the country. Public availability of data also greatly depends depending on the country, mostly for depleted fields. So aquifers also. In some countries, like Spain, is very complete, for some others not. So it's not even among countries. And line caverns are not included in this. So it can be improved. About capacity estimations. So in porous media, there were works, for instance, from the gas industry through Gas Infrastructure Europe and Gaidao's company that converted the capacity of natural gas storage to hydrogen. And in a higher spray, you also had kind of the same approach, looking at what's the capacity of natural gas storage and convert that to hydrogen. There is also a history of overestimation in some fields that are closely related, either for CCS or also for shale gas. Sometimes when you only look at it from a purely geological point of view, you can make some big overestimation of the capacity, and it has been done in these closed industries. So we had to try to be careful and to follow the SPE methodology on resource, but we still have this risk. And on salt, there was this master thesis by Nikolaus Weber and published in Kaglayan et al. Paper that was already giving some European scale capacity estimation of the storage capacity in salt. So the main development is that we used the geological database, and we computed, we did simplified analytical models using basic properties like porosity, surface extent, thickness of the reservoir, etc. And for each of the 800 traps, we made a capacity estimation of the storage potential. So now that's available, that's released, and that's done at the European scale. So this is the difficulty here. So the limitations is that it is based on this geological database. It has all the limitations I exposed before. It is storage performance. Also, we kind of miss industrial experience in hydrogen underground storage with this very low viscosity, highly mobile gas, and we would benefit from field scale lessons learned on porous underground hydrogen storage. And we could not do dynamic simulations to really test the capacity on the 800 traps. We only validated through 22 traps, but it will be required this kind of dynamic approach to have a more and clearer estimation. Also, I did not mention, but we compared that with three real real reservoir models of underground natural gas storages, and the simplified approach we applied matches what we had with this detailed modeling. Microbiological risk assessment. So you know, I guess, or you will know probably later today, that hydrogen is a very strong reductor. In abiotic conditions, reaction would happen thermodynamically. It will maybe at high temperature, but it is stopped below like 200 degrees C due to kinetics, but some microorganisms use this potential thermodynamic energy for their own metabolism and trigger the reaction. And this is what we have mostly, the risk we have in our storage. We see that it has happened in Lobodice, for instance, in historical town gas storages. So it has been characterized at lab scale, and what is Hystories bring here? I introduced that. It is this kind of idea of having a large sample from 12 natural gas storage sites, brines. So we took samples. We characterized the families of microorganisms that were identified, and we identified H2 consuming families of microorganisms in all but one samples. Then it was enriched. It was tested under high pressure and almost room pressure and high temperature. And we monitor the consumption of hydrogen, the production of byproducts of these enriched brines. And then we tried also to model static models through Frixie, and then use it in dynamic model reservoir at reservoir scale to try to go from the reactor scale to the field scale, and this is, I think, one of the big challenge. And another thing that is a result of the project is this chart at the center of the screen, done by MicroPro, and it's a kind of ranking flow chart to assess the risk of the risk for the reservoir of having too strong microorganism activity, and you can see that it's only based on reservoir characteristics. Family of microorganisms that are or are not present is not an entry in this table, in this chart. It's the idea is to rank, because this can change. This is hard to evaluate, and so this is why it is based only on characteristics that are characteristics of the field: salinity, temperature, availability of carbon sources, and of sulfate, I think. So this is still highly site-specific. This approach was based on this sampling and on the literature available. We call for enlarging and continuing this approach of large-scale sampling, a little bit like what has been proposed in High Life project. And also we call for more lessons learned and data from over long time. From especially in porous media pilots. On material and corrosion, so in an underground storage, wells, especially in porous media, wells are the main man-built structure. It's a very standardized industry. It relies mostly on API standards. And these API standards do not cover hydrogen. There are surface standards that do cover hydrogen, like ASME B3112, but they rely on surface way of doing, like over thicknesses that are not applicable in these well conditions. So one thing we also relied on a quite large and extensive lab program at University of Leoben. And we took more than a lot of steel grades, carbon steel, stainless steel, a lot of different steel grades. We tested them, and we tested the uptake of hydrogen in the steel crystal. We tested the loss of mechanical properties, and we found out at the end a quite clear two table with some recommendations based only. It's a research project. A very experimental one. So based on this research results only, we derived this kind of table with recommendation for each steel grade. It was also done in connection with the industry, in connection with steel manufacturers. And for instance, this topic changed a lot, I think, in the last 2 years. And we can see that some of the major manufacturers, like Vallourec, and kind of clearly took position during the project, quoting results and reports of this project to make a clear recommendation on the steel grade they recommend for hydrogen storage applications. So Vallourec was the first one. Another manufacturer of casings also publicly recommends now a steel grade, and it changes a lot. And I think it's a very good example of what research can bring and how it can be transferred to the industry. So it changed a lot for casings, but we are still in a pre-normative approach. It's not standardized yet. There is no public standard. I think we're not there yet. It is also moving for other parts of well equipment. We heard Ali Burton presentation yesterday for safety valves packers. Some manufacturers are proposing solutions now. It's maybe not that as clear as it is now for casings. We have some also other manufacturers, Hartmann for wellheads, others that are like kind of proposing clearly solutions, but it's still pre-normative. It's still we don't have standards, and it's not as we cannot really proceed as we do for natural gas storage. And then there is the fact that wells aren't all new. And there is still a more open question on the way of doing for re-qualifying existing wells. So now I will move to the techno-economic findings very fast. Okay. So about permitting, so we developed a review of the maturity of administrative of regulatory readiness at European scale based on surveys. We also did a first assessment of the environmental footprint of developing a new hydrogen storage site, and we tested through surveys the acceptability or the perception of developing a new underground storage site. I went through that quickly in the introduction. We had this model that helped us to develop a demand, a view on the demand of hydrogen underground storage. It's published. We also developed a cost estimation model because we lacked a detailed one and a hydrogen-specific one. And we draw costs that are based on capacity, euros per megawatt hour of storage, but a big part of the storage is driven by the flow rate you can apply to the storage. So we have actually not one cost, but several costs. One that is related to the capacity, one that is related to the flow rate, and it's probably the only public source of information that is giving that today. And it's done for salt and porous media, and it's based on a clearly defined project-based cost estimation, a clearly defined site, because boundaries are not very clear always. And we then applied it. I will go to that on several case studies. So it was based for it was a basis for the cost estimation of case studies. And these case studies also looked at the market opportunities for 5 countries in Europe. So quickly, we find, as said by Hadi, high similarities between natural gas and hydrogen. There are differences in physical and chemical properties, hydrogen embrittlement, reactivity, lower viscosity, but there are also other differences for deployment, because we are looking at deployment at a European scale from the start, and our networks were developed nationally. We are looking at development in a very short time frame, decades, not over centuries. We are also looking at development not even having a clear business case, which is not the case for natural gas. And also we are looking at development in the 2030s, 2050s with an attention to environmental footprint, to social embeddedness that was not there 20 years or 50 years ago. So there are differences. The overview we have is that hydrogen storage in salt caverns is seen as mature. However, this is only true from the technical side, but these 3 other points, they're still true for hydrogen deployment. And we don't see either an obvious showstopper for hydrogen deployment in depleted fields or aquifers, even if there is a question of gas purity when withdrawing, or gas treatment cost, and also on gas on the specifications, because this will impact the treatment that will be needed. So this is the call I listed, and just to finish on how Hystories can be used for the deployment. First deployment, when in the call it was seen as whether or not we should proceed with a pilot at the end of Hystories, where actually at the end of Hystories there are already 6 pilots. So it kind of went way faster than expected, and implementation is now understood as implementation of this energy system at large scale. And with the gas industry in particular is looking at it, as published for the TSO, this hydrogen backbone vision. For the larger gas industry, including distribution operators, this H2 inframap vision, and even including more general the hydrogen economy there is this hydrogen corridors vision of hydrogen flowing in Europe, etc. So there are some people that are bringing this vision of deployment at the industrial scale. And Hystories can help by saying, for instance, well, for all countries, we estimated the demand under many hypotheses. We estimated the capacity in porous media. We also have this in salt caverns. And one of the findings is that for nearly all countries, technical capacity is much higher than demand. And you don't even have to look offshore. Onshore is sufficient. And this is true for both salt and porous media. We also, on each of the trap, we estimated, so we will need to rank sites and to select only a few of them. So we developed a cost estimation of developing storage, either for seasonal or fast cycling storage, and a suitability mark for each of the traps, because it is very site specific. And really last slide. We have, it is site specific, but it is local. So we have put this data on a GIS. It's available on our website. So thank you. Sorry for being over time.
No, thank you very much, Arnaud. I think, yeah, I mean, as you said, you could fill hours of presentation, and we would certainly not get bored. We can take one big question, Hardy says. I follow the boss. Any quick question to Arnaud, or we leave it? We can come back in the discussion. That's it.
Your site selection analysis, is it the database? Are you going to release it public, finally?
Yes.
But that's
So this GIS that I presented, it is actually public on hystories.eu/map.